Hello everybody, this is notes number 36, compound interest and the number E. Yes, I said number E, not letter E. So in this video, we're just keeping it really short and I'm giving you the formulas and we're doing an example. I know some of you have requested shorter videos. I made a different video where I explained how we get these formulas, so you can choose to watch that if you want to. If you choose not to watch it, then you're just not going to see how we get these formulas. Okay, first I'm going to talk about the number E. E is known as the natural base. It's named after a mathematician named Euler, which is actually spelled E-U-L-E-R. It's Euler's number. And its exact value is the limit as n goes to infinity of 1 plus 1 over n to the nth power, which I explain in the other video. And the approximate value is 2.718. So just like the number pi, which we think of as approximately 3.14, the number E, it's irrational, so 2.718 is not exact. This is used a lot in things like exponential growth of populations, of bacteria, which I guess is also a population, exponential decay of things like radioactive substances, growth of money, and so on. To find E on your calculator, there's two different places. So you'll notice that you have this button next to the 4 that says LN, and we're going to learn what that means soon in this chapter. Above it, you see e to the x. So you can press second function, e to the x, and then if you just want e, make it e to the first power, and there you see the approximate value. Or if you wanted e squared, e to the x, and then put your exponent in there, and so on. Oftentimes when we're using e, we end up raising it to a power. On the other hand, another place to get e is right above the divide. So see, it's the second function of the divide, so you can press second, divide, and then there's e. Okay. So in the other video, I explained to you how we get the compound interest formula. So you'll want to write this formula down. Compound interest means you invest a certain amount of money, you earn interest on that money, and then you leave your money in the bank so you continue to earn interest, and you end up earning interest on your interest, and your money compounds. So there are two different formulas. This one is the non-continuous formula, where compounding is happening annually or semi-annually or daily or monthly, a finite number of times per year. And the other formula is continuous. We'll get to that in a minute. So A represents your final amount of money after T years. P represents the initial amount of money invested, which we call the principal. R is the interest rate as a decimal. N is the number of times the money is compounded per year. And T is the number of years. Here's the other formula for continuously compounded interest, and once again, the other video explains how we get this formula. A is still the final dollar amount at time t. P is still the initial dollar amount, the principal. Notice we have the number E in this formula. R is still the interest rate as a decimal, and T is still time in years. So here's the example we're going to work through, and we'll get to use both formulas. Suppose $3,000 is invested at a 5% annual interest rate for 10 years. How much money will the investment be worth if interest is compounded annually, semi-annually, monthly, and daily, and continuously? So for parts A, B, C, and D, we're going to use this formula. A equals P times 1 plus R over N to the NT, because that's the non-continuous compounding when you have a fixed number of times per year. And for part E, we're going to use the continuously compounded formula, A equals PE to the RT. So back to part A, we're finding the final amount. See how much money, that's the final amount. So we're finding A. The amount invested is $3,000, so that's P, the principal. The annual interest rate is 5%, so as a decimal that would be 0.05. And N is the number of compoundings per year. If it says annually, that's one time per year. And the exponent NT would be the number of times per year times the number of years. So 1 times 10 is 10. So we put this into a calculator. Now you can simplify and just write this one as 3,000 times 1.05 to the 10th. Put that into a calculator and round to the nearest penny. 3,000 times 1.05 to the 10th power is $4,886.68. Let's go through that again for part B. 3,000 is our principal. We have 1 plus 0.05 divided by 2 because semi-annually means 2 times per year. Raised to the power of 2 times 10. 2 times a year for 10 years, so that's the 20th power. So then let's put that in the calculator. 3,000 times 1 plus 0.05 divided by 2, raised to the power 20, and we get $4,915.85, rounded to the nearest penny. So you can see it was the same amount of money invested for the same amount of time and the same interest rate, but when you increase the number of compoundings, you increase the frequency upon which your interest is earning interest, and so you get a little bit more money. Let's go with monthly. Monthly would be 12 times per year. 3,000 times 1 plus 0.05 over 12, raised to the power 12 times 10, or 120. Put that in your calculator. And we get, rounded to the nearest penny, $4,941.03. Daily. For daily, we use 365 days in a year. So we're going to put that in place of n. And then put that in the calculator. And we get approximately $4,945.99. So you can see that even though the amount of money is going up, the amount of increase isn't huge. So going from 12 times a year to 365 times a year, it did not dramatically increase the amount. It's not like eventually you'll have $1 million. There is a limit, and we find this limit by doing the continuously compounded interest. This gives us kind of like a cap. Even if you were able to compound infinitely many times per year, there's a maximum you can get, and that's what we're going to find with this formula. So we have 3,000 times e raised to the 0.05 times 10. Now you can see the way I've written it out with my parentheses, but if I'm putting this in the calculator, I just want to open parentheses before the 0.05 and close them after the 10. If I open and close, the calculator doesn't understand what I'm doing, and it won't put the 10 in the exponent. So let's check that out. 3,000 times e raised to the power 0.05 times 10. This is why we use the e to the power button, because we typically do raise e to a power. $4,946.16. It's not going to get any better than that. Okay, here's your homework, and you have some compound interest formula problems that were in section 7.1 and some that are in section 7.3, and then these problems here have to do with working with the number e. Thanks, everybody.